development of bipedal robot STOB-v3 and reinforcement learning-based locomotion control considering a single rigid body model. Concept design commences with a simplified model based on existing STOB-v2 data. The simplified model's learning results confirm that the primary joint torques remain within the target range. We selected an actuator meeting the torque target and verified its reliability. Based on the concept design, the detailed design was carried out as follows. STOB-v3 is a 10° of freedom bipedal walking robot. It is a child-scale platform approximately 1 meter tall, with each leg consisting of a 5° of freedom joint structure that omits the ankle roll joint. This block diagram summarizes the STOB-v3 electrical system architecture. A 48-volt to 12-volt to 5-volt stepped power rail with modular, switch-isolated distribution for fault containment and maintenance, plus wireless remote operation and joystick-based command. Key mechanisms improve torque delivery and contact robustness. Each leg is indirectly driven via a 4-bar linkage, with the bar-type foot compensating for the omission of ankle roll. Perform gravity compensation to revalidate the consistency between the physical robot and the model, as well as the reliability of actuator inputs and outputs. Reinforcement learning only framework. Our baseline is a model-free, RL-only controller. The policy maps proprioceptive observations and commands to joint PD targets. The baseline policy was deployed to the STOB-v3 and forward walking was performed on flat ground. A strong forward drift tendency was observed during walking in place. To improve stability, we integrate SRBM into the RL controller to compute physically consistent GRF and landing targets from the estimated state and desired accelerations. A QP then enforces friction and force limits, producing a feasible contact wrench that guides the policy. SRBM-QP Guided Reinforcement Learning Framework. As shown in the block diagram, the SRBM-QP Guided RL uses SRBM computed references only during training for privileged critic inputs and reward shaping, and it runs standalone at deployment without solving the QP. The SRBM-QP guided policy was deployed to the STOB-v3 and forward walking was performed on flat ground. When comparing in-place walking, the SRBM-QP guidance policy reduced the mean error in linear velocity by 36.43% in the x direction and 10.6% in the y direction, 23.49% in angular velocity, whilst the landing impact peak decreased by 4.34%. Finally, the SRBM-QP guided policy was deployed on the STOB-v3 and freely walked. SRBM-QP guidance reduces landing impact and drift compared to the RL-only baseline, combining physically consistent SRBM references with RL robustness. Current limits include hip roll torque saturation and limited torso sway control without a waist joint. Next, we will refine the hardware and SRBM-QP and benchmark against WBC.